All right, friends, welcome to Chemistry 352 via Zoom. I'm sorry about this, but as I said, I woke up with a cough and didn't want to spread whatever it is I have. In any case, for answering questions, feel free to use the chat function. I'm not sure how easy it is for me to see if you've got your hand raised, so the TAs will be online moderating the chat, and if there's a question that I need to answer, I'll pause and we'll try to go from there. Okay, so last time we're talking about ester hydrolysis under basic conditions, which is called saponification. And the reason this is called saponification is because it's the way that you make soap, or one of the historical ways that you can make soap. The idea is that you take an ester and react it under aqueous conditions with a really strong base, hydroxide. And hydroxide is strong enough to attack the carbonyl directly to get a negatively charged tetrahedral intermediate. At that point, electrons could kick back down and kick off the OH group as a leaving group. That would just be going backwards to the previous step, but it's also equally favorable to kick off the OR minus group. And here's the thing that makes it go all the way forward. Once you kick off that OR minus group, you have a carboxylic acid. And that carboxylic acid then reacts irreversibly with the OR minus group from the ester that you just kicked off, because most of these OR minus groups are going to have conjugate acids whose pK is around 16 or higher. And so it's definitely feasible for the OR minus group to remove this proton. That's an irreversible process by a factor of about, doing math here, maybe 100 billion. So that proceeds irreversibly to give us this carboxylate. We can use that carboxylate as is, or we can gently acidify the solution at the end and recover the carboxylic acid. The details to that are not necessarily important. I do want you to know this mechanism and know the saponification reaction. But one of the key reasons I want you to know that is because this is involved in how our ancestors made soap. So you may not have known this, but fats and oils are called triglycerides, and they are actually triesters. So you have this 3-carbon triol glycerol in which each of the oxygens is connected to a long chain carboxylic acid. We call that a fatty acid. And it's usually anywhere from 16 to 18 carbons long. Sometimes there are double bonds in the carbon chain, and we'll get to that later. But there are 3 of these carboxylic acids linked to the glycerol molecule via ester bonds. Okay, so you have glycerol, you have esters, and then you have this long chain fatty acid. And this is a very nonpolar molecule, which is why fats and oils don't mix well with water. Our ancestors were able to treat fats and oils obtained from animals or nature with something called lye. And lye is basically potassium hydroxide, and you can get that from wood ashes. So any of you church history buffs out there, in Kirtland today, the church has restored the old ashery, which was a place for generating lye in order to make soap. So when you expose this fat or oil to hydroxide, the same thing happens that I've shown you earlier. you have hydroxide attack one of the carbonyls to get a tetrahedral intermediate. And then that, and I'm not going to show you the rest of the steps because they're right here. It's exactly the same, only we're using different R groups, okay? But when we're done, we liberate the triol, which is glycerol, and that has some important uses. I don't know that our soap making ancestors did anything with it, but the really useful thing is the long chain fatty acid carboxylate that you get after the saponification reaction. 2, 4, 6, 8. All right, that's an 18 carbon chain. And what you have here, and you may have learned about this in like chapter 3 of 351, you have a polar group on one end of the molecule, and then over here to the right you have a non-polar tail. And molecules like this will self-assemble in water to generate micelles. And what do micelles look like? Well, the polar head groups are all oriented out towards water because they can interact with water molecules, and then the non-polar tails are all in the interior. And these micelles are great carriers for oil and grease because other oils and grease molecules can be sequestered in the inside and become water soluble because they're carried inside this micelle package. So that's a great historical use of ester saponification for things that have affected our day-to-day lives, and we're a lot cleaner and less smelly because of soap. So congratulations. Most soaps today are not fatty acids. The head groups are a little bit different, though you still can use long-chain fatty acids as soap. Another thing is that nature uses the glycerol. See if I'm making stuff up. Nature uses a glycerol molecule modified with 2 esters, but not 3. This is called a Diacyl Glycerol, and any of you who are in cell biology may have encountered this as the acronym DAG. Sometimes nature will elaborate this other oxygen with some other things. So, for example, you can have something like that. I'm probably getting that wrong, so I don't want to. Nature will put a phosphate group here, and then something else here. And this molecule also has, a polar head group and 2 nonpolar tails. But the shape is different because instead of having a polar head group with 1 nonpolar tail, you've got 2. When you have just 1 nonpolar tail, the general shape of the molecule is sort of conical. So that fits nicely into a micelle. When you have 1 polar head group and 2 nonpolar tails, the shape is more cylindrical. So I'm just going to show you, and this, what we're going to draw now, is probably the way you've seen these molecules illustrated before in other classes. Notice that when we have 2 nonpolar tails and 1 polar head group, that the general shape is cylindrical. And so instead of self-assembling into micelles, these what we're going to draw now is probably the way you've seen these molecules illustrated before in other classes. Notice that when we have 2 nonpolar tails and 1 polar head group, that the general shape is cylindrical. And so instead of self-assembling into micelles, these, 2 nonpolar diacyl glycerol lipids assemble into what are called bilayers. The individual lipid molecules assemble side by side, and then another sleeve of lipids will assemble on the other side. And this can extend off indefinitely in both directions, and that's called a lipid bilayer, and that's the basis of membranes for our cells. And of course, over a long period, if the lipid bilayer is large enough, it can curl back on itself and make a cell membrane. Okay, questions so far about that application? Anything you want to ask? Okay, well, I'll be looking at the chat, so if you have one, feel free to type it in. Another thing that I want to talk about in terms of ester hydrolysis is how enzymes do it. So, and this gives us a chance to introduce something called the catalytic triad. And the type of enzyme that hydrolyzes the ester bonds in lipids is called a lipase, because it takes a lipid and it hydrolyzes it. Okay, so you know that the fat or oil molecule looks like this, right? For our purposes, if it's okay, I'm going to abbreviate these both as R groups to sort of make it easier to draw what we're going to draw. So here is the glycerol molecule, and here is one of its carboxylic acids. And we'll just maybe label this in green and this in purple according to the color scheme we used above, just to remind ourselves that this is the glycerol portion and this is the fatty acid portion. Within the lipase active site, there is a pocket that the carbonyl oxygen packs into. And that pocket is lined with hydrogen bond donating groups. Squiggly lines here indicate the larger enzyme molecule. But these amide bonds, these amide NH protons, create a hydrogen bonding environment for the carbonyl oxygen that activates it towards nucleophilic attack. So think of this as just sort of the pocket that the carbonyl packs into, and already, even before attack, there is hydrogen bonding. And the reason this activates the carbonyl, I suppose you could ask, well, why doesn't nature just protonate the carbonyl fully? And I suppose it could. But this strategy just uses hydrogen bonds, and the effect is similar to protonation, right? And in reality, there's not a huge amount of difference between this situation and this situation. That is, there's not a huge amount of difference between the oxygen having the proton or the nitrogen having the proton. All right. So, and this is called, and you'll learn about this in biochemistry, the Oxyanion Hole, because though it does interact with the carbonyl oxygen, it interacts even better with the negatively charged oxygen in the tetrahedral intermediate. So when enzymes go to hydrolyze esters, it turns out they don't use water directly. They use a stripe of 3 amino acid side chains called the Catalytic Triad. And it's worth knowing about because it's interesting to see how nature creates bases that are strong enough to attack carbonyl compounds. So this amino acid is called serine. That's not important. You don't need to memorize it, but I want you to recognize it in the future when you hear about these things. This amino acid is called histidine. And then this amino acid is called aspartate. It's the conjugate base of aspartic acid. Okay, so these residues are all located very close to each other, and their proximity and their presence in the active site allows for things to happen that you wouldn't necessarily normally expect. In other words, pKa's of functional groups can be different in an enzymatic active site. So serine, the enzyme is going to attack the ester of our fatty or our lipid using this serine, although it's currently neutral and maybe not nucleophilic enough to attack. So what nature does is it uses this nearby histidine side chain to remove this proton. When that proton is removed, then serine is nucleophilic enough to attack and get you attack the carbonyl carbon at the pi star and generate a tetrahedral intermediate. And what makes histidine nucleophilic enough to do that, remove the proton from serine, is this aspartate nearby removes the proton from histidine. You know what? I drew that structure incorrectly. I hope you can forgive me. We remove this other proton from histidine. The aspartic acid side chain removes that other proton from histidine, and that allows for the nitrogen here to be nucleophilic enough to remove the proton from serine. So you have this relay of protons. It's called sometimes this catalytic triad is called a proton shuttle, but it's all about making this serine nucleophilic enough to attack the carbonyl carbon. So after this step, what you've got is the OR group, you've got a tetrahedral intermediate, you have the long hydrocarbon chain, and then you have this serine residue. And I'll draw what the catalytic triad looks like after we've, So here's the serine. Histidine is here. And then aspartate is here. And if we're following the protons that go where, we just had this chain that shifted the protons over. Question from Hayden: do histidine and aspartate not attack the carbonyl because they aren't close enough? Exactly. Yeah, the active site positions the serine in just the right place relative to the carbonyl and the oxyanion hole. I haven't drawn that oxyanion hole here. Maybe I'll just do it quickly so that you get the idea that we're hydrogen bonding with that tetrahedral intermediate and stabilizing it. So at this stage, what happens is we're going to kick off the glycerol group. We're using purple for glycerol. We're using green for the fatty acid. We're going to kick off that glycerol group, and on its way out, it's going to pick up a proton from histidine, and which is itself going to pick up a proton from aspartate. And that sort of resets those groups to do additional proton shuttling. So after that reaction, we no longer have a tetrahedral intermediate. We have the serine side chain now in an ester with the fatty acid. Glycerol is now free. And if there are other fatty acids on the glycerol molecule, they can go on and be hydrolyzed as well. And then what we're going to do, let's see. What we're going to do next is notice that the histidine and the aspartate are reset now as they were at the very beginning with the yellow proton on histidine. The only thing is that the blue proton left with glycerol. And notice that the fatty acid is not liberated. It's liberated from glycerol, but it's now connected to the enzyme. So this so far isn't ester hydrolysis. It's called esterification, meaning we made the fatty acid go from one alcohol to another. What needs to be done at this point is that you have water act as a nucleophile, and sort of water becomes the source of the new proton. And you have histidine remove the proton from water, then OH can attack the carbonyl carbon to give you a tetrahedral intermediate. And what makes that possible is that aspartate goes ahead and steals the yellow proton from histidine again, which is what makes that histidine nucleophilic enough to attack. So I'm not going to draw the remaining steps of that molecule or of that process because it's going to look exactly like what we've done over here, only at the end, the thing that's going to get kicked off as the leaving group is this serine side chain. But this is how this catalytic triad does the work. All right, Kaylor's mentioning that it isn't that these residues aren't close enough, it has to do with the pKa's. Yeah. By passing the protons back and forth, and by the fact that these individual three residues are close enough to each other, it turns out their pKa's are adjusted to the point where all of this is reasonable. You would not necessarily expect a histidine residue whose conjugate acid has a pKa of 6 to be able to remove a proton from a serine residue which has a pKa of 16. Nevertheless, it happens, and we pay for that by the enzyme active site creating a close environment and by the fact that these three are all close together. And there's a lot more to unpack there. There's some controversy around hydrogen bonding and something called really low barrier hydrogen bonds, but we're going to sort of ignore all of that. All right, any other questions that you want to talk about lipases? Okay. I will point out that once we're skipping a few steps, but at the very end, you will have liberated all of the carbons of all of the OHs of your glycerol molecule. In biology, you can actually use this as starting material for new lipids, or alternatively, you can do a few oxidation and phosphorylation reactions, and this can be shunted into glycolysis. In addition, the liberated fatty acid can then go on to be metabolized via something that's called fatty acid beta oxidation, and we'll talk about that in a couple of weeks. And that's how that's the whole process of burning fat. Okay. So we're talking about the most difficult reactions with carboxylic acids. We started this discussion with making an ester from a carboxylic acid. And recall that the challenge was with the carboxylic acid that if your nucleophile is a good base, you're dead in the water, because instead of attacking the carbonyl carbon, you're simply going to remove a proton from the carboxylic acid. And then, woe is me, I'm never going to get my ester worlds without number, right? So when we did ester formation with carboxylic acids and alcohols, we had to use an acid catalyst. Okay, question from the group, are we responsible for knowing that mechanism then? You are not responsible for memorizing these side chains, and aside from the structures of these side chains, what's going on here is simply ester saponification, or ester hydrolysis. So I think that part of the mechanism, what's going on with the ester, is important. I'm not necessarily going to hold you responsible for what's going on with these groups. Okay, but they will in biochem, so for what it's worth. Analogously, if you wanted to take a carboxylic acid, if you wanted to take a carboxylic acid and then react it with some amine, to get the desired product, the desired product here is an amide, where it's a dehydration type reaction. You would envision the nitrogen attacking the carbonyl carbon, getting a tetrahedral intermediate, swapping who swapping who's the good leaving group, and so on to do the substitution reaction. But instead, because amines are decent bases, what happens is the basic amino group attacks the proton, and you get the carboxylate and the corresponding ammonium ion, and again, you're sort of dead in the water. Your text mentions, and I totally ignore, the fact that if you make this salt, the negatively charged carboxylate and the positively charged ammonium group, and then you heat them up to really high temperature, you can actually get the amide to form. And the reason I'm neglecting that is because nobody does that. That process is not synthetically useful for the vast majority of organic compounds that we deal with. High heat tends to result in degradation, and so we need another strategy. And we can't use acid catalysis here because the acid catalyst would protonate the amino group to the ammonium, and instead of protonating the carboxylate to the ammonium. So we need a different strategy. It's going to be similar to acid catalysis in that our ultimate goal is to convert this OH group into a good leaving group that doesn't have an acidic proton. So let me show you a couple of ways this is done. One of the sort of simplest ways, though I don't think it necessarily works for all molecules, is to convert acid to an acid chloride using a reagent called thionyl chloride, or SOCl2. I think you encountered this in 351, where you saw that it was able to convert OH into a chloride. It does so here, though the mechanism is perhaps not perhaps not as important as you might think, and so I'm not really going to talk about it. You end up with an intermediate. I'll show you the key intermediate so you can get a sense for how this happens. The oxygen from the carboxylic acid from the OH group ends up bonded to sulfur, because sulfur-oxygen bonds are more stable than sulfur-chlorine bonds. And at the same time, chloro attacks to get this tetrahedral intermediate. And what causes the acid chloride to form is that the group that leaves is a fantastic leaving group. And the reason that's a fantastic leaving group is it can degrade rapidly as it's leaving into your acid chloride, SO2, which is a gas and bubbles away, and then Cl minus. And so the key thing that makes this reaction work is that it's irreversible. I wanted to show you this mechanism because it was not, sometimes I feel like if I don't see the mechanism that I don't really understand what's going on. But I'm not going to test you on the mechanism for SOCl2 modification of a carboxylic acid. But just know that it works because of this step, and the effect is to replace OH with Cl, and now you've got an acid chloride. Okay, and then once you've got, so that would be step 1, converting the carboxylic acid to an amide. Step 2 then would be to have the chloride now, which is a good leaving group but doesn't have an acidic proton, encounter the amine. So once you've purified the acid chloride, you have the amine attack. Now, I suppose we could argue at this point whether the amine can attack the acid chloride directly or whether you need to protonate first. These reactions, it turns out, work without acid catalysis. And so presumably the acid chloride is electrophilic enough due to the electron withdrawing nature of chlorine and the weakness of the carbon-chlorine bond that the amine can attack directly, even though that's something we wouldn't have done earlier. Nevertheless, if you decide to show me a mechanism where you're somehow protonating the carbonyl oxygen before the amine attacks, I'm not going to penalize you for that. So try not to worry too much. At this stage, it turns out we need a little bit excess amine because there's a proton on the nitrogen of the amide that we need to get rid of. So in your text, this is usually add an excess of amine, and I don't require you to write that you have an excess. I'm just going to assume that you know that, but that's for removing the proton from the positively charged nitrogen. And that gets you to this step. Now we don't have a, now the nitrogen is no longer a good leaving group. Before, it could have left as a neutral amine. Now, if it left, it would leave as a negatively charged nitrogen, which is really bad, really unstable. And if you want to see how that's the case, go look up the pKa of this amine converting into its conjugate base, the negatively charged amide, and it's not good. So chloro is really the best leaving group we have here. And so electrons kick down, chlorine leaves, and that step is basically irreversible because chlorine is such a good leaving group. And in the end, we have this amide group. Okay? So notice the overall effect of these reactions that I'm showing you. The overall effect is to substitute the amine, substitute the amine for the OH group via the acid chloride intermediate. And the reason we did it this way is because the amine can't attack the carboxylic acid directly because it would just get protonated. All right. All right, I'm looking at some of the questions online. Question is, could we have used a protecting group such as the silyl ether to protect the OH group of the carboxylic acid? That sounds like a reasonable strategy, and in some ways, conceptually, that's what we're doing with the acid chloride. I haven't seen people use silyl ethers with alcohols, and I'm not sure why, so I kind of have to punt on that question. Okay, others? All right. These types of reactions where we swap out one group on a carboxylic acid derivative from the other for another group are called nucleophilic acyl substitution reactions. But you don't need to think of them as a separate kind of reaction. This is similar to everything we've done since the beginning of this semester. You have a carbonyl compound. Sometimes you have to do something to it to make it reactive enough for a nucleophile to attack. Once the nucleophile attacks, you get a tetrahedral intermediate. What happens next depends on whether or not there's a good leaving group. Sometimes you use proton transfer to switch who's the good leaving group and so on. So I want you to see this all as additional manifestations of the same basic principle. Let's see, this question from Ben, could the Cl- deprotonate the positively charged nitrogen here as well? It's possible your book shows that, though that seems unreasonable in the sense that Cl- is not a very good base. Its conjugate acid has a pKa of -7, so it's more reasonable for an amine to do. And really, this is the reason why you have to add excess amine. You are technically right, though, in the sense that at the end, the byproducts that we have that we aren't worrying about is an ammonium ion and Cl-, which is kind of like an amine and HCl. Excuse me. Okay, so I want to show you another more common way of converting carboxylic acids. And I think the issue is thionyl chloride is a pretty reactive reagent, and not every organic molecule can tolerate that reagent. In acid chlorides are also very reactive, and so not every molecule can tolerate having that reactivity without reacting with itself. So this is a method that works to make an amide, but I'm going to tell you, we make amides all the time in my lab, and we never do it this way. So I'm going to show you what your text shows you, which is a second way of making an amide bond. Of course, approach number one is to make the acid chloride first, and then attack with the amine. Approach number two is to use a Carbo-Diemide, which I realize is going to mean nothing to you, but in the business we call this a coupling reagent because it promotes the reaction of a coupling of an amino group with a carboxylic acid. And everything I'm going to show you here is just all about, remember, don't get lost in the details. It's all about converting the OH into something that doesn't have an acidic proton but is nevertheless a good leaving group. Okay? So what does this Carbo-Diemide reagent look like? Well, it's a strange reagent in that it has carbon bonded 4 times to nitrogens, and that functional group is called Carbo-Diemide. And then each of these nitrogens is itself bonded to another carbon. Okay, this is called dicyclohexyl Carbo-Diemide, or DCC. There are a number of other sort of boutique reagents that look a lot like this, but that function in basically the same way. Usually, along with DCC, we use a non-nucleophilic base. Because there are going to be protons that need to be removed to to push the reaction forward, but we don't want this base to be anything that can attack the activated carboxylic acid. So an example of a non-nucleophilic base is triethylamine. This is a tertiary amine, and the reason it's non-nucleophilic is because, for example, if it were to attack some carboxylic acid derivative that had a leaving group on it, once you get to that tetrahedral intermediate, notice there's no proton there that can be removed to stop that from being a good leaving group. And so that's sort of permanently a good leaving group. And so we can use this as a base without worrying about it interfering with the reaction. Okay, so the effect overall is to take a carboxylic acid and an amino group. You use DCC and triethylamine. It's possible, I don't remember, that your text neglects to put the base in there, and if it does, that's fine. It's okay if you forget that. The overall effect is to connect the the carbonyl of the acid with the nitrogen of the amine in an amide bond. And the products that come from this, the byproduct, what happens to the reagent, the Carbo-Diemide reagent after you're done, is that it converts into this really stable, really inert functional group. Molecules that have carbons bonded to carbonyl carbons bonded to two nitrogens are called urea type molecules. So this is dicyclohexyl urea, and it's very stable. Its formation is irreversible, and it drives the reaction forward. Makes the reaction irreversible. So how does this work mechanistically? I'm going to show it to you because I feel like, again, sometimes if I don't see the mechanism, I'm gonna forget what the reagent does. That being said, I don't think I'm gonna test you on this mechanism because it's a little bit convoluted with extraneous details that are not really on the theme of attacking carbonyl carbons. So our non-nucleophilic base first removes a proton from the carboxylic acid to give us this negatively charged carboxylate, whereupon that negatively charged carboxylate attacks the carbon of the diamide reagent, and it's attacking one of the two carbon-nitrogen pi stars. So this is basically like carbonyl chemistry. We're breaking one of the two carbon-nitrogen pi bonds and picking up, let's see, I should do this better. Picking up a proton on the resulting nitrogen from some acid group. Maybe it's another carboxylic acid, maybe it's the conjugate acid of this base. We don't care. When that happens, we get this intermediate, and you can think of all of this as a good leaving group. So at this stage, the nitrogen of the amide can attack, and it's nucleophilic enough to attack directly, in part because of how reactive this reagent is. By the way, if you sort of squint at this intermediate and look at it sideways, it sort of looks like an anhydride. You've got two carbonyl-like groups bonded to each other via an oxygen. in any case, after you do that, you have this situation. I'm going to abbreviate all of that as good leaving group. We need a proton transfer. And it turns out we don't need an extra base to do that. I'm going to show you what this looks like if I draw out the structure. This is the part that always confuses folks, and so I don't want to make a big deal out of it. It's cool enough, though, that it might be fun for some of you to see. If not, feel free to ignore it. Let's see. Notice that here's the nitrogen that attacked as a nucleophile. Here's our tetrahedral intermediate. Here's the good leaving group. We want the nitrogen to stay, so we need to deprotonate it. But it turns out the leaving group can do that as it's leaving, because the atom that's going to get protonated in the leaving group is 6 atoms away from the proton on the amino group. And that makes a nice 6-membered ring transition state that's pretty easy. That's pretty easy to react in sort of a concerted fashion. So electrons kick down to kick off the leaving group, and at the same time the carbon-nitrogen pi bond breaks, and these lone pair electrons on the nitrogen remove the proton from the amino group. And what we have left is our amino group that's present. And then, like I showed you, we have that dicyclohexyl urea as a byproduct, which you can easily separate from the amide. Okay? So what do I want you to know about this? What's going to be on the test? I expect you to know how to use this reagent in a synthesis to convert a carboxylic acid and an amine into an amide. I expect you to know with broad brushstrokes what this reagent does. That is, turn the OH into a good leaving group, and then the nitrogen attacks. There's proton transfer so that the nitrogen can stay and the leaving group leaves. So I want you to be familiar with that conceptual series of steps. However, I don't really care that you know how to draw this. I think this freaks a lot of people out. It's not as bad as you think it is. It's just a lot going on at once. And so maybe to help you one more time see conceptually what's going on, this is our leaving group. This is the nitrogen that we have attacked. This oxygen, by the way, is the one that was in the carboxylic acid. So that actually becomes part of the leaving group. And then all that's going on here is, as the leaving group leaves, it steals, as what would have been a negatively charged leaving group leaves, it steals a proton from the positively charged nitrogen, and that allows you to get to these neutral products. Okay. Questions? Okay, I think that's probably enough for today. When we return next time on Monday, we're going to talk about how biology makes amide bonds. We're going to review all the nucleophilic acyl substitution reactions you can do with acid chlorides and anhydrides. That's reactivity of acid chlorides and anhydrides is pretty easy. I think you can get it in the text and in your study guide without a lot of in-class explanation. I want to spend our class time talking about the really difficult stuff and also on interesting biological applications. We also next time will talk about how beta-lactam antibiotics work. These are the penicillins and so on. All right. With that, have a great day, and I will see you Monday. I will let you know via email whether on Monday it's going to be via Zoom or in person.